Okay, we're now ready to look at integrals that contain the expression a squared minus x squared, where a is some constant, x is our variable here. It could be that you have the square root of that. It could be that you have this raised to some power other than the square root, or it could just be a squared minus x squared. Okay? When we have integrals that have this form, what we may do is make the following substitution. So we're going to let x be equal to a, that same a there, sine theta. Now we're going to be dealing with the inverse trig, so remember what we're restricting ourselves to is negative pi over 2 to pi over 2, because that's the standard restriction on sine when talking about an inverse. So this is going to be what we make our substitution on. And the identity that we will likely use in this scenario is 1 minus sine squared theta equals cosine squared theta. So that's one of our Pythagorean identities. Okay, now note, if we make x equals to a sine theta, then dx, or how the rate that x is changing, is related to theta in the following way: a cosine of theta d theta. All right, so this time we're going to be doing like inverse substitution. So let's start with an example and go from there. So let's say we have the following: the square root of 9 minus x squared over x squared dx. Now first, whenever you're looking at a integral problem, you should always do a quick scan of, can I simplify this? Is there an obvious u substitution? Neither of which I can see here. And I want you to note something over here that I know no one would ever make this mistake, but let's just be clear that the square root of a squared minus x squared does absolutely not equal to a minus x, right? The radical does not distribute over a sum. Also, the square root of x squared doesn't equal x. It equals x only if x itself is positive. What it does equal is the absolute value of x. Okay? All right. So back to our example here. So this is of the form a squared minus x squared, where my a is 3. All right, so I'm going to make the following substitution. X is equal to a, oops, sorry, not a, 3 sine theta. This means that dx is equal to 3 cosine of theta d theta. All right, so now let's plug everything into every x we see. We're going to replace it with 3 sine theta, and dx we're going to replace with 3 cosine theta d theta. All right, so then this integral becomes the square root of 9 minus 9 sine squared theta all over 9 cosine squared theta, because that's my, oops, sorry, that's not true. It's absolutely not true. It's 9 sine squared theta, because that's still just x on the bottom. And then our dx is 3 cosine theta d theta. Okay, so we've done all the substituting, and hopefully when we simplify, it's going to be much nicer. Now note that I can factor out a, well, one thing we could do is, well, let's go ahead and factor this out. So if I factor out a 9 from this radical on the top, I end up with the square root of 9, which is 3. That can come out, and I'm left with 1 minus sine squared theta over 9 sine squared theta, and then times another 3, so I'll put that 3 squared there, cosine theta d theta. Now I see my 9's cancel on top and bottom. All right, here's where we're ready to use this identity here, that 1 minus sine squared is equal to cosine squared. So let's go down another level. So this is the square root of cosine squared over sine squared, and then times another cosine theta. That was a cosine squared d theta. Okay, now be careful here. So remember, this is what I was pointing out to you. The square root of cosine squared theta is actually equal to the absolute value of cosine theta, which is equal to cosine theta itself if cosine of theta is greater than or equal to 0. And it's equal to the opposite of that if cosine of theta is less than 0. But remember when we made sure that we restricted our domain to negative pi over 2 to pi over 2 because we were perhaps going to be discussing the inverse sign? Well, note that on that interval, let's draw the cosine graph. Looks like that, right? So our cosine graph on the interval from negative pi over 2 to pi over 2 is in fact positive. So it's because of that that we can take the square root of cosine squared and replace it with just cosine theta. But in general, you can't do that. Times cosine theta d theta, or cosine squared theta over sine squared theta d theta, which is equal to cotangent squared theta d theta. Now, this is not an known antiderivative, right? This is the case, it's very similar to like tangent squared. And remember the process is when we have even power on tangent, right? So what I'm going to probably do here is switch this using the identity, the Pythagorean identity attached to cotangent squared, and convert this to cosecant squared theta minus 1 d theta. Those are equivalent by the Pythagorean identity. Now, this one does have a nice antiderivative. It's just negative cotangent of theta. And then minus 1 is minus theta plus c. Now, just like before, we never leave our answer in terms of the variable that we substituted. We always want to go back to our original answer. So this is why that triangle that we drew mattered. So let's come down here. Let's kind of switch colors for a minute and draw the triangle that's associated with the substitution that we made. X equals 3 sine theta is equivalent to x over 3 is equal to sine theta. Okay, so this generates the following triangle with ratio x over 3, there's your theta, which means this side is 9 minus x squared. All right, so our substitution, x equals 3 sine theta, generated that triangle, which now we know all 6 trig functions, and in particular, negative cotangent of theta. So cotangent is adjacent over hypotenuse, and we want the negative of it. So negative square root of 9 minus x squared over x. And then theta is going to be, well, this is, since we restricted our domain, it has an inverse here, and it is sine inverse of x over 3 plus c. Capiche?